All right, good morning, Solana. I'm Brennan Watt, VP of Core Engineering at Anza. I'm joined today by Kevin Bowers, the architect behind Firedancer. And today, we're talking IBRL. That's the increased bandwidth, reduced latency mantra that aligns all Solana developers toward a common goal. Solana built a brand out of being the high-performance chain with low fees. Being decentralized and permissionless are mere table stakes. They are not an excuse to be slow or expensive. And users and developers have been coming to Solana and staying because of the user experience this high-performance blockchain architecture delivers. Today, we'll peek into the engineering taking place on Solana, powering that core base upon which everything else is built. Anza is the company behind Agave, the successor to the original Solana Labs client and the dominant validator client since inception. Building efficient, resilient, performant clients is what we do best and an integral part of the Solana success story. But there's a new validator client in town that's making waves. And this is probably a good time to hand things off to Kevin to say more about that.
Cool. Thanks, Brennan. Since Brennan already introduced me and gave a brief overview of Agave, I'll jump right into a brief overview of Firedancer. Firedancer is a new Solana validator in development in the open at the above link. Early hybrid versions of Firedancer, we call Frankendancer, have been running on testnet since late 23 and on mainnet since mid-24. These have grown to represent about a third of testnet stake and a little bit over 6% of stake on mainnet as of last night. When I was first asked to work on Firedancer, my initial role was to organize various wish lists into a practical development plan with measurable deliverables. To better understand the goals of Firedancer, let's look at some oversimplified versions of these wish lists. First, while Foundation wanted everything in a pony, their top priorities were to foster development of an open, independent second validator and to make the chain operations enterprise grade. Though Anza had not yet spun off at that time, the second wish list I characterized as theirs. They've been the most vocal with us about supporting a worldwide community with a 50 billion account capacity stretch goal. The next wish list I characterize as the operators' communities, but it is universal. If one of our production systems goes down, the revenue it generates stops, but its associated costs continue. We care deeply that our systems stay up and our costs stay down. This exact dynamic applies to the operator community. They care deeply that the chain stays up and their costs stay down. The last wish list I characterize as ours, but it is implied by the other wish lists. Consider a hypothetical chain tracking 50 billion accounts that requires validators to verify accounts sequentially at startup. Further, suppose the best off-the-shelf software on the best commodity hardware verifies accounts at a seemingly fast 100,000 accounts per second per core. Restarting the chain would take almost a week. Looks like we need high-speed parallel cryptography for high reliability. Consider if that same chain had a 100 transactions per second capacity. Just touching each account once would take over 15 years. Looks like we need high-speed transaction execution for high scalability. The community needs to be thinking in terms of millions of transactions per second if it wants to be competitive with traditional applications. It's a good bet that in the weeks to decades waiting for this hypothetical chain to start and then touch an account, an enterprising developer would realize all the performance doesn't matter magical thinking they've been taught is a lie, and would whip up a new chain designed from the outset with real-world performance in mind, and be able to do so in less than a decade. In fact, we don't have to take that bet. It's already happened. One of the reasons for our interest is Foundation deeply grokked this. They cared about performance from day one, and it showed in the data. Solana was the fastest chain by a wide margin when we started. Our technical specialty is distributed computing at speeds most people don't think is possible, much less needed. Contrary to conventional wisdom, though, this is not a weird affectation. Price-time exchange order matching rules create an economic dynamic where we need to make ultra-high performance distributed systems to survive in ultra-competitive traditional financial markets. We've always thought our role here is to push the protocol to the limits of the laws of physics and information theory to make it a viable platform for real-world applications. This graph of commits versus time shows that since then we've been doing the work and at an accelerating pace. Now, high speed is all about optimizing data flow. Data flow is the very first thing frozen in an application implementation. If it isn't optimized up front, the only way to significantly improve performance later is to throw everything away and start from scratch. Unsurprisingly, then, the first thing we did was streamline a validator's data flow. This shows the high-level data flow through Firedancer when it is the leader. The large box represents a commodity server. The smaller boxes are CPU cores and network interfaces on that server. The top half receives raw transactions, filters out duplicate transactions and transactions with bad signatures, and packs valid transactions together for execution. The bottom half schedules valid transactions, executes them as parallel as possible, and distributes the resulting blocks to other validators to verify execution was done correctly. We've been running along this data flow, incrementally replacing Agave components with in-house developed ones. We call these early hybrids Firedancer. Given our limited time, here's a few milestones relevant to increasing bandwidth and reducing latency. At breakpoint 22, we live demoed a software transaction receive pipeline with a 1.2 million transactions per second receive capacity and a 0.6 million signature verifications per second capacity on an old stock GCP host. Shortly afterwards, we stitched our software pipeline into Agave to make the first Firedancer. Mid-23, we live demoed to Anza and Foundation a hardware-accelerated 1 million signature verifications per second capacity at lower cost and lower power than CPUs and GPUs on an old stock AWS F1 FPGA. We also live demoed using 8 of these FPGAs to scale signature verification capacity to roughly 8 million verifications per second per host. We've made this technology available to 00. Not too long after, external partners started experimenting with Firedancer on testnet. At breakpoint 23, we showed methods to dramatically improve the efficiency of many common cryptographic encoding operations and how to enhance validator security without sacrificing performance. Mid-24, we live demoed to Foundation and Anza roughly 100 modified Firedancers running on commodity hosts distributed over a 25 gigabits per second data center local area network and a 100 gigabits per second intercontinental wide area network, a proto-00, processing just over 1 million simple uncontended transactions per second. By this time, Firedancer was very close to the full Firedancer, much more so than the community realizes even today. It was already using our own kernel bypass networking, core-to-core communications, quick implementation, signature verification, block packing, parallel transaction execution, accounts database, proof of history, Reed-Solomon encoding, turbine block distribution, and so forth. The main remaining Agave components were the Solana runtime and consensus. This demo showed that we can configure Firedancer to make the most out of whatever hardware and network is available, and we can scale it beyond the limits of the protocol and user demand for foreseeable future. Just as important, the demo showed that with minor modifications, Agave can do so too. Ongoing work is not about tuning performance further. It is about replacing the last remaining Agave components to realize the Foundation's primary goal of having a second completely independent validator implementation, and testing and auditing and testing and fuzzing and testing and testing and testing. Given how close Firedancer and Firedancer are already, we expect the transition to Firedancer to be seamless. There's no reason for operators to wait to try it out, and we encourage them to kick the tires. The TLDR is that we're the hipsters of IBRL. We were increasing bandwidth and reducing latency before it was cool. Now, there's been a lot of worry in the community about what will happen if there are multiple validators with different performance characteristics. One reason for open sourcing Firedancer was to educate the community about how to optimize a validator. Shortly after this demo, we did deep dives with Anza and Foundation about the protocol, Agave runtime, and Agave consensus modifications that we made. Suffice to say, we're not worried, and this is a good place to hand the reins back to Brennan to see why.
At Anza, we're taking the performance messages that Kevin just covered to heart. And in case you haven't noticed, the network is looking really nice right now from an engineering perspective. This chart shows over 3 years of historical slot latency data. And slot times are under 400 milliseconds. I'm guessing most people didn't even know that was a thing until the Agave v2.1 release. And this is essentially a measure of how efficiently our block and transaction pipelines are operating. We need to get transactions into blocks and blocks out to the validator network as seamlessly as possible. Any stalls getting transactions into blocks, streaming microblocks across the network, or verifying state can interrupt these pipelines and cause delays. And that's the ugly truth of the left side of this picture here. I much prefer the glorious right side that we're operating in today. And this is one of the only charts that we like to see down and to the right. Skip rates are under 0.5%. A skip is any time we had a chance to build a block, but didn't for whatever reason. And this might be due to things like offline hardware, slow leader node transitions, or network partitions. And we can think of this like yield loss in a factory. Yield loss hurts user experience, it hurts IBRL, and it hurts validator economics. The closer we can drive yields to 100%, the better it is for everyone. And this trend is absolutely phenomenal. I mean, look at that chart. It's just chef's kiss. Transaction confirmation latencies are way down, with many transactions achieving single slot latency. And this is a measure from the time when you send a transaction on the client side to when the block that it gets included in is confirmed by the network. In this chart, each point represents one transaction. And as you can see, the majority of them are well under 1 second. This is light years ahead of where we've been in the past. And this is absolutely crucial for user experience. This is what is really driving how snappy the applications can be. And we want to drive this even lower and unlock new use cases. I'm not going to go into this more now, but trust me when I tell you that the Anza devs are absolutely cooking. And finally, we're consistently filling blocks to capacity. This chart shows when we modestly increase maximum transaction capacity, and even after this increase, we're constantly bumping up against that limit. We often have more transactions than we have capacity in blocks to include them. And this is the type of problem that we absolutely love to have. There is real demand for inclusion on Solana. And so obviously, all of these metrics look great. We're really excited about them, but the job is not finished. Solana is fast, and we love that it's fast, but other people see that it's fast, and they see how much we're winning, and they want to experience that too, so they're coming after us, and we cannot get complacent. But it is in our DNA as Solana builders to be aggressive. And so at Anza and Firedancer, we're committing to keeping the pedal to the metal and making it rain block space this year. I'll say it again. We are going to make it rain block space this year. And these are not sleight of hand promises that can only be delivered in some test environment. There are no caveats, there are no asterisks, and this message will not be watered down by the time it hits real users on mainnet. We're increasing capacity where it matters, for the complex types of transactions that users are actually performing on mainnet today. These are things like complex program invocations, contended state updates, and of course, token swaps. So how are we going to do it? This brings me to the more technical part of my presentation. I know we've got like a bit of a left curve audience here. Left curve is kind of nerd speak for anyone that doesn't wear tech hoodies 5 days out of the week. But I promise I'm not going to get too crazy. I just want to cover a few of the very most important things happening on Agave this year. So the first of which is aggressively reducing memory allocations. Old Agave is that traffic jam on the left-hand side, just drowning under a sea of extraneous memory allocations, page faults, and M-advice storms galore. Not great. But we've been exercising the allocation demons that have ailed us, and we're in a much better place now. But there's a ton more work to do. Thousands of micro improvements that each on their own might not turn the needle much, but collectively add up to giant gains. And that's really been the story of the last 2 Agave releases, and we expect that trend to continue. The second one I'll mention, sticking with this theme of micro improvements, is just tightening up latency on the hop path. The hop path is that critical piece of code that gets exercised for every transaction or every shred in a block. And sometimes we like to think of working on performance kind of like Neo in the Matrix, and we're bending the fabric of space and time, or that it's all this sexy whiteboard algorithm redesign. But in reality, it's a lot of blood, sweat, and tears. It's a little more boring, and honestly, it's a bit of a grind. And at Anza, we've had to get back to basics and reevaluate things like how efficient are our hashing algorithms? How often are we serializing data into and out of these complex types? And I know this is super boring stuff, but it's the stuff that actually makes a big difference when you talk about performance in production. And at Anza, that's what we're all about, working to improve real performance in production every single day. The third thing that I'll mention is Turbine. Turbine is the name of the Solana block propagation protocol. And this is how we get block data from the leader node out to the validator network. And we use a little tree that looks something like this. But there are a couple important distinctions between this toy example and real mainnet. The first one is the number of nodes, or the rectangles in the picture, which in this toy diagram is 9, but in reality on mainnet is around 6,000. And the second thing is the level of fan out, which is the number of arrows coming out of each rectangle, which is only 2 in this picture, but on mainnet is 200. And oh, by the way, that fancy new consensus algorithm that we're rolling out, Alpenglow, with that, we want to dramatically increase the amount of fan out to reduce the number of network hops. More fan out, fewer layers, lower latency. But the upshot of all this is that poor relayer node at the top of the tree is getting stressed extremely hard. On mainnet today, we're asking 150K network IOPS out of our high-stake validators. That's 150,000 packets per second just for Turbine every second of the day. And we've had to overhaul the Agave network design to be able to make this happen. And finally, let's talk about the scheduler. The scheduler is the brain that decides which transactions make it into the block. And it's overgone several iterations over the years. We've had to change it to do things like make sure local fee markets actually work, improve efficiency and performance, and highly optimize for the real workload that we see on mainnet. We need to keep those execution cores humming and those block rewards flowing. That's the name of the game. And we expect this critical component to continue to evolve. At Anza, we're paving the way for innovation here by allowing operators to compete in the marketplace with well-aligned incentives. And so we're extremely pumped for all these changes and upcoming improvements to Agave. But let's zoom back out here, because there are a lot of things happening in the broader development community to get excited about as well.
Thank you. Thanks, Brennan. Though widely available commodity hardware can support millions of transactions per second scale capacity on a host, the surrounding ecosystem needs work to expose it. About a year ago, I was asked to present lessons we learned in Firedancer development at an offsite with Anza and Foundation. I collected these lessons into the amazing stories of Firedancer. One story was pure IBRL. A gigabits per second attack is a you problem, but a terabits per second attack is a we problem. A validator doesn't exist in isolation. There are many validators, and they communicate with users and with each other via wide area networks. A public schedule advertises when each validator is the leader. When a validator is not the leader, it verifies votes and blocks produced by recent leaders. We effectively have a ring of transaction filtering resources and a ring of transaction execution resources. The connectivity between these rings is currently limited. Filtering resources on a validator can only be used to feed execution resources on that validator. For the reliability and scale wishes, then, each validator needs enough resources by itself for whatever user capacity and denial of service attack resilience is desired for the entire chain. This spikes hardware network requirements towards high-end hosts and high-end data centers with high-end network connectivity, ignoring the efficiency wishes of the operator community. Even though we have more filtering resources than we need in aggregate, they aren't in the right place at the right time. The rings aren't connected flexibly enough. It's not hard for a malicious user to send enough junk from multiple sources to the current leader to overwhelm its filtering resources. The leader's high-end network provider will not care because their high-end fiber optic connections are capable of handling terabits. 10 gig or 25 gig knocking over just one of their many hosts does not impact their many other customers. That is, a gigabits per second attack is not their problem, it's your problem. If we pull apart the rings and connect them more flexibly, the current leader could make use of the entire chain's filtering resources. We no longer need to provision each validator for the whole chain's filtering needs. 00 recently started up to foster the development of network acceleration technologies and community wide area networks optimized for decentralized protocols like Solana. We are eager adopters, contributing network bandwidth and filtering hardware technologies. By using optimized multicast wide area enabled networks, transactions and blocks can be distributed faster and more reliably. By using the network and hardware more efficiently, operators can support more users and give them a better experience with their infrastructure. By using distributed hardware filtering, denial of service attacks require many terabits per second, hitting many geographically sites simultaneously. This is not an attack against you. This is an attack against everybody everywhere. That is, a terabits per second attack is a you problem, is not a you problem, it's a we problem. From our perspective, this is not a new idea. The internet is not well optimized for big tech or traditional finance. They use their own internal custom wide area networks optimized to their needs. It is great to see things like 00 start to level the playing field for decentralized applications. A second independent validator has many benefits beyond performance, but performance is a prerequisite for increasing bandwidth and reducing latency. Optimizing connectivity is just one of the areas we are working with the community to improve the whole ecosystem. Brennan touched on several others in which Anza is doing the same, and it's great to see the recent proposals for consensus, multiple leaders, and so forth, many discussed this week, push even more aggressively to streamline and decentralize validator functionality. Since we don't have more time, I'll conclude by noting my background is high-performance scientific computing and traditional computational finance, not crypto. As a newbie assembling the wish list at the start of Firedancer, it was clear to me the community wanted to grow and maximize people's agency. It wasn't clear the necessary performance was possible, and it wasn't clear the community was ready to make the necessary changes if so. It's now clear to me that this is not just possible, but happening. With that, I'll hand the reins back to Brennan.
This tech is here today, and it has real legs. Transaction volume and speed are accelerating. New use cases and possibilities are coming online every day. A shared, unified state spanning DePIN, gaming, real-world assets, stablecoins. We implore you not to take it lightly. Solana is ready to compete with big tech and traditional finance, and we can't stop, won't stop IBRLing. As you can imagine, there's a ton going on behind the scenes at both Anza and Firedancer that we couldn't get into today. In classic IBRL fashion, we'll keep the latency of this presentation short and get back to shipping and iterating. We don't do roadmaps, we do releases. It truly is ship or die. All right, thanks for listening. Tune into, follow us on X to keep up on all things Agave and Firedancer. Tune into the blogs. And as always, the real alpha exists in plain sight on GitHub. All right, thanks everyone. Thanks.